So we start from the Bohr theory itself. So I think you guys have already studied about the Bohr theory in chemistry, right?
Yes, sir.
Yeah. So first of all, what is the limitation? What are the limitations of Bohr theory? When we should apply and when we should not apply?
Sir, it is only applicable to uni-electronic systems like He plus
Correct.
H.
Correct. So it is only meant for the single electron system.
Bohr's atomic model.
So hydrogen by default is a single electron system. Helium is not by default. So if we remove one electron by making it
Helium plus, yeah.
He plus, then it will come again a single electron system. And with lithium, we can remove two
Plus.
electrons to single electron system. And then for beryllium, we can take
E plus.
three electrons, and then it will become single electron system. And therefore, we should be able to apply this the theory, which is meant for the single electron system. So in the Bohr series, there are many assumptions, and based on these assumptions only, we are going to get the answer. Okay, so
The
these are
hypothesis.
so we do have the hypothesis, and we have to follow those hypotheses in order to, I mean, apply this theory to selected scenario. Later on in the X-ray chapter, we'll try to generalize the Bohr theory to a multi-electron system with some modification, and after that, we'll derive the Moseley's equation. And after that, we'll remove all electron from the atom. We'll make a nucleus, and then we study about the nuclear physics, that how it works. So we have multiple stages of learning. So we'll start with the Bohr theory. From there, we'll set up the agenda. We'll go for the X-ray. From there, we'll go for the nuclear physics. And in the nuclear physics, we'll study about the radioactivity. And then at the end, we'll study about the EM wave, the electromagnetic wave. And that will almost culminate the modern physics part of our course. So to begin with the postulate or the hypothesis, now what are the postulate? When we say postulate, what we mean by postulate?
Postulates are the theory, not theory, assumption.
Those are some rules stated by the person who made the
So they
theory.
are just
Yeah, it is like, of course, you cannot prove the postulate, but once the postulate is taken for granted, then things further will be or may simplified and can be proved or can be done some experiment upon to verify the theory, underlying theory in this same you can say given postulate. So once you make the postulate, then you can justify the further claims. Okay, so these are, you can say, a very it's like a hunch, it's like a intelligent guess, and based on this intelligent guess, we can actually do the further prediction. That's why we call postulate. So we have Einstein postulate, we have the Bohr's postulate, and we have so many kinetic theory of gases is also a
Euclid's
postulate.
postulates.
Yeah, of course. So in Bohr's theory, what are the postulate? So first of all, the first postulate is that the motion of electron around the nucleus is taken in a circular orbit, which is not the case, of course. But we are going to discuss here a particle nature of atom. So there are two ways of thinking. One is the cloud nature, like the electron gas format. Other is the particle format. So Bohr is started with the particle format. Okay.
You are talking about the wave and the particle electron can be both
Yes. Yes. So what Bohr said that the nucleus is, of course,
at the center.
containing all the masses, and it is acting as a center. And he assumed the planetary motion of the electron around the nucleus in a circular path. So this circle is your postulate part. So circle is not the true path of the electron. I mean, in fact, the
It's
electron,
elliptical.
yeah, yeah, it's just like assumption. Like you assume circular path. Then Sommerfeld came and he said, no, the path is elliptical. Okay. And now all those theories are invalid today. In today's date, we all have the quantum theory only. But knowing the historical background is quite important because it gives some insight about the behavior of electron atom and how they interact. So every atom will have the number of protons depending on its atomic number. So we can say the number of positive charge or the charge in the nucleus is equals to Z multiplied by E. E is the charge on electron. It's not a negative charge, it's just a value of charge, and we call it electronic charge. And this is 1.6 into 10 power minus 19 coulomb that we are aware of. So depending on the atom use, let's say you can use H atom, so Z is 1. If you can use He to Li 3, Be 4, so we can have an answer 1, 2, 3, 4. So to generalize this, we write it Ze. Now the electron is a negative charge and nucleus is a positive charge, so definitely they will attract. Now which law will define the force of attraction? So the force of attraction between the two charges we define by the Coulomb's law, right?
Electrostatic law, yeah.
So here we talk about the Coulomb's law, and this Coulomb's law will be equals to 1 upon 4 pi epsilon naught into Q1 Q2 by R square. R is the separation. So the Coulomb force is simple, 1 by 4 pi epsilon naught Q1 Q2 by R square. And what you can understand here, that, and of course the medium within the nucleus and the electron cannot be anything, so it is perfect vacuum. This is perfect vacuum because the medium is made of atoms, so inside the atom we have perfect vacuum. Do you realize this? So when you say medium, then you say collection of atoms. So when you go inside the atom, what we have is perfect vacuum, so there's nothing there. So we can write 1 by 4 pi epsilon naught. The first charge is Ze, which is charge in the nucleus. The second the second is the force experienced by the electron, and because it's a single electron system, so we can say that this is the only force acting. This is the net force acting on the electron. So this is E, and the separation is square, R square. So because of the circular assumption, things are pretty easy. Now we can apply the dynamics of circular motion that we have already studied. And what is the dynamics of circular motion? So this is the attractive force which is acting towards the center.
is equal to mv square by r.
Exactly. So now we know that this is circular motion, so we can write net force towards the center equals to MAC. And this you can either write as V square by R, or you can write as omega square. So depending on what you want to derive, you can write. So the first assumption was the circular orbit was the first assumption. Circular orbit. So now what is the second assumption, which is the most important part of this Bohr series?
So angular momentum is equals to nh by 2 pi.
Exactly. So this is called the quantization of angular momentum. And definitely when we say quantization of angular momentum, here we talk about the orbital one, not the spin. Because spin is anyway constant, so not an issue. But here the orbital is taken as constant. And the quantization is means it is discrete. So when I say it's quantized, we say this is a discrete value. In fact, in microscopic world, everything is discrete. Continuity is a phenomena of macroscopic world. And therefore, quantization is the essential, you can say, part of learning any microscopic world. So why this discreteness? The question is, what is the discretization of this angular momentum? So for that, we need to go to a chapter which is not taught to you, and maybe some of you have studied. and the concept is called the concept of stationary wave. So if we have a string, and if I assume that this string is attached to the two ends, and if you set this string into oscillation, then let's say you struck this string on the left end, and this creates a wave which transmits towards the right, and upon reflection from the right boundary it comes back, and in this due process of coming back they superimpose, and as a result they establish something called stationary wave or standing wave. Now once the standing wave is established, then the energy gets confined within particular limit. Just a minute. So now the wave is going towards right, and upon reflection, we do have a wave towards left. And when they get superimposed, then you can see there is a bundle of energy. The energy in this location are kind of confined, or you can say, think this is like a uh, okay. So now this is like a discrete, and now when we say discrete, it means the energy is kind of confined in, you can say, a spatial region. So if we have some spatial region, and if you can finite, make the energy finite in this region, so we say this is discrete. Now the next region will have its own finite energy. The next region will have its own finite energy. So this is what we mean by discrete value. So when we talk about the photons coming, I mean, as a virtue of light. So light is a collection of photons. Photons are nothing but the collection of discrete packets of energy. So this will have some energy. This will have some energy, and these energies are discrete. It means they have finite value, and this value, if you know, is h nu from the Planck's theory. So in atoms, how the discrete energy can be created? Okay. So in Bohr's theory, we see the discreteness. I mean, we don't see the discreteness. We just see the orbits. Okay. So how Bohr explained that in case of oscillation, we can have different mode of oscillation. Now, what do we mean by mode of oscillation? If those who have studied the waves and sound, they know. So you can set this into oscillation at different frequencies. So this is the simplest mode of oscillation. Just one loop. It can have two mode of oscillation. The second mode of oscillation like this. The third I have shown in the left side. Then it could be 4, 5, 6, or it could be infinite. The mode of oscillation is that the frequency value. So as the frequency will increase, the mode of oscillation will increase, and you can see multiple loops in the standing wave. And more the frequency, we can also say there are like a lot of energy which is confined in these packets. So in atom, how to define the same? How to describe the energy part? Okay. So Bohr said that these energy parts are nothing but the orbitals, or orbit, you can say orbits. So when you look at the one orbit, actually that is analogous to one energy state, and that is the theory. Okay, so there is nothing like orbit. I mean, orbit is just a fictional character in this Bohr's theory, but this fictional character is understood in this way. So one orbit is one fictional character in the Bohr's theory, and that is representing the one set of energy. So as you go from away from the nucleus, you go into a territory of different energy levels. and that is just a hypothesis. Like, I mean, of course, nothing like that exists in the real world. Okay, so this is how Bohr imagined his own understanding of atom. That was his PhD thesis, and he won the Nobel Prize for the same. So, what happened? I mean, there is a history behind this. I mean, let me tell you the history of Bohr's theory. So, what happened that when Rutherford gave his theory of atom, he said that okay, electrons are moving in a circular orbit, and because of the classical theory of physics, if something is orbiting, it is accelerating, and we know that every acceleration leads to the radiation of energy. And if there is a radiation of energy, then there is a loss of energy, and if there is a loss of energy, then the electron eventually get attracted towards the nucleus, and it will collapse with the nucleus, and therefore the atom should be unstable. Now that is not the case. We all know that atoms are stable. So that was the kind of deviation from the physics of classical nature to today's physics, which we call quantum physics. But that time quantum was not there. That's very interesting. So that time everyone was researching about the light. Okay. Now, if you know about light, in light we study about the hydrogen spectrum. Okay. So everyone was studying about the hydrogen spectrum, and why they were studying. That's very interesting. So when sunlight is coming to Earth, and if we put that sunlight through the chamber, which is consisted of only H atoms, we got some missing lines. We got some dark lines. Now, what do you mean by dark lines? So let's say light is coming from some source. So let me demonstrate a lab meaning of sun. Let's say this is sun, and this is my chamber. And this chamber is consisted of the H atoms. Now, when the light is passing through this chamber, on a screen on the other side, what we got is some missing lines. Some lines was like missing. You can say dark spot. And these dark spots were very much like a discrete lines with a small bandwidth. So we call it H spectrum, and this is called the absorption spectrum. So we call it H alpha, H beta, H gamma, H delta, something like that. The next one. Now the question is, if you're throwing a light through a gas, what do you expect? Generally, we expect the same light here appearing everywhere, correct? But instead, what we are getting is some missing lines. So now the question is, why selective lines are missing? Why selective piece of spectrum is missing? So we can say that that is missing because selective piece of energy is being absorbed by the H atoms. Because if H atom will absorb everything, then nothing will appear on the right side. If H atom will absorb nothing, then the full light will come. But if light is coming with some missing values, some dark lines, it means only selective values are getting absorbed. So that led to the phenomena called discreteness. Like now, that was the turning point in the history of science, that Bohr realized that okay, this missing lines is indicating something is discrete in behavior. So what he did was that the numbers which he got, so Bohr's got these 4 numbers, and he took, I mean, went to his friend in England to meet his very close friend called Balmer. So he met his friend Balmer, and Balmer was a mathematical genius. So Bohr gave him just 4 numbers, like these missing values, and he asked Balmer that, can you find something relevant with these numbers? Is there any pattern? And within few minutes, Balmer came with the fantastic formula in which all these discrete numbers were related with each other, and that led to the discovery of quantum. So now that was the like turning point in the history of science. Like Bohr realized that okay, things are discrete at a microscopic level, and therefore the atom do not follows the classical theory of physics. Okay, so that was like turning point. He realized that okay, no, the classical theory, the continuity is not the phenomena of the micro world. Something discreteness is there, and from there he derived the entire the Bohr's theory, and then he, to justify his claim that this is a situation, he said that the discrete energy levels are static in nature. And when we say static, it means stationary. And this stationary energy levels are called orbit. So when you say orbit, there's nothing physical orbit. The orbit is just a analogy to the, you can say, the energy values. So one energy value is representing one orbit. So this is symbolic only. I mean, you do not take it granted. Okay, this is something of, I mean, a physical orbit. So it was a very poor theory in regard to the development of science in today's world, but because that was the beginning, so that was the biggest turning point, and therefore it was recognized, and in fact he received the Nobel Prize for the same. So everything is started with the light actually. So we were searching about light. From there we got the H spectrum. From the H spectrum we got the missing lines. From the missing lines we realized discreteness. From there we went back to the number, and then from there we postulated the quantum theory. So it is a reverse process. Now in physics, the discrete energy levels are defined in terms of stationary wave or standing wave. That is the basic understanding of Bohr's theory. So if you want to understand the standing wave, you need to go back to the chapter of wave and sound. And because for many, I haven't taught the chapter, it will be taken care later on. So as of now, I'll assume that, okay, you know this chapter, and then I will proceed accordingly. Because anyway, the modern physics is the last topic. So generally I expect that everything is done, right? So today we are going to derive the Bohr's postulate actually from scratch. So the postulate of Bohr, which is the quantization of angular momentum. So what he said that every orbit so only those electrons are like allowed to move in the orbit which possesses the finite energy or fixed energy, as against the Rutherford theory in which the orbiting electron will radiate the energy. The Bohr said no, only those electrons are like allowed or permitted who can maintain their energy, can keep their energy fixed. If we have this nucleus and if we have electron here, now this orbit represents one energy value. Now if you go to the next level, this is the new energy value, and so on. So theoretically, how many orbits we can have?
The infinite.
Infinite. Now there is some principle called the Bohr's correspondence principle, in which if n tends to very large, then you enter the macro world. So you leave the micro world, you enter the macro world, and in the macro world the discreteness disappears, and what happens? The continuity follows. Okay, so that is a different theory. So here we'll try to establish that how the standing wave will form by electron. So the problem is you cannot make a wave with particle, correct? So here comes the wave nature of particle. So we are all aware of the de Broglie wavelength. So what is de Broglie wavelength? So de Broglie said that every particle must exhibit some wave-like character, because Einstein said that every wave can also behave as a particle-like character. So light is having dual nature. So light is having dual nature, which means light can behave as particle or behave as wave. Okay. So what do we mean by particle and wave? So when Einstein said light is a particle, it does not mean a physical particle. So here particle refers to the concept of confinement of energy. So when we say that energy is confined in a certain space, we call it particle. And the wave refers to the non-confinement, something which is spread universally. So that is the only difference between the particle concept and wave concept. It has nothing to do with the particle of physical nature. So when I say light is a particle, we are trying to say that it is the localization of energy, and that localization of energy Einstein termed as particle, and one should not get confused with the physical nature of particle, because these two are totally different things. Okay. And when it comes to wave, the wave concept means something which is spread throughout, which is not confined. So the delocalization of energy is called wave, and the localization is called particle. Okay, so let's say if we open a tap and then water is flowing, we can say this is wave because it's continuous. But let's say in a Holi, if you put a water in a balloon and if you throw, then of course you're throwing the water in the discrete packet. So we can say this is particle. So particle and a wave only differs in terms of localization or delocalization factor, nothing more. Is this clear?
Yes, sir.
Yes, sir.
So now what is de Broglie said that a moving particle will have momentum. So if a particle is moving with velocity v and particle will have some mass m, it will have momentum mv. And if you have momentum, it will have some wave-like characteristic. It will have some wavelength. So from where that energy relation comes, so for that I have to go back to the Einstein theory, in which he proved that energy of a particle, okay, energy of a particle is given by mc square whole square, okay, mc square whole square plus p square c square. Understood? Now what does it mean? You can see this is a square equals to m square c power 4 plus p square c square. P is the momentum. Now this is for a in general particle. For massless particle, for massless particle, which is, you can say any wave is like any electromagnetic wave is massless, the m becomes zero. M here is the rest mass. Basically, m is the rest mass, not the mass, the rest mass. For massless particle, m naught is zero, which is called the rest mass. And those who don't know, so there are two types of mass. Is this is called the rest mass. That mass when it is not in motion, we call the rest mass, and this is called the relativistic mass. Okay. So m naught is zero, which is the rest mass, and once you make m naught zero, what will get the relation? This will give you E square equals to P square by C square. So we can say E equals to P. Sorry, what I'm writing. E square P square. And therefore, can we write E equals to PC? So momentum is basically energy upon speed of light. Okay. So therefore, for any electromagnetic wave, this is the relation. Momentum is energy upon speed of light, and we know that energy for the wave we can write as h nu or sc by lambda, and if you divide by c, what you get is h by lambda. So from here we derive the formula that momentum is h by lambda. So now what it is saying that anything which is having momentum must have wavelength, the reverse process. Now in case of electromagnetic wave, we know that momentum is h by lambda. So in the reverse case, you can say that anything which is having momentum must have some wavelength. So if we put into that picture, then what we got is called the de Broglie wavelength. So the lambda is associated with the momentum of particle, and when you do it for the particle, we call de Broglie wavelength. Is this clear? So a particle having momentum will have lambda. Now the problem is in the real world scenario, the mass is very high. So let's say if you talk about the lightest particle which you have seen in your life, will have some mass, at least in microgram. Now that leads to the wavelength which is so small that cannot be detected. So imagine a momentum of 1, like let's say mass is 1 kg and velocity is 1 meter per second. So momentum is 1. In that case, lambda is as good as h. And how small is h?
6.626 into 10 raised to minus 34 joule second.
Now can you imagine this wavelength? Minus 34. Now if you know the visible spectrum, it only goes from the roughly 3800 angstrom to 7800 angstrom, correct?
Yes, sir.
Now
Yes,
this
yes.
wavelength we are able to detect it, and this is how small. This is just minus 7. Not 34 is can we detect at all? No. Which means the wavelength for any real world particle which is not moving really fast, we cannot detect. We cannot detect. So until p is not very small, this number will not become meaningful or observable, you can say. And that is why in the real world, the wave character is totally, you can say, suppressed by the particle character of the macro world. But if you go to the sub-elementary particles, the particles which are very light in weight, let's say electron. So what is the mass of electron? Correct. So mass of electron is this. And not only that, the velocity of electron is quite close to c. Now, if you put velocity of electron as just 10 power 8 meter per second, let's say it is less by 3 factor. Or if you want, you can make it slightly less, let's say 10 power 7 only. In that case, what we expect the wavelength? Let's see, check it out. 9.1, 10 power minus 30, 31, and 10 power 7. Now this will lead to minus 3, this is minus 10, right? So this is now getting something, some angstrom, right? Some angstrom. Correct? You can see this is minus 10 power. So now we are getting the value which can be observed. Now this falls under the, you can say, territory of the human made observations, and therefore this can be detected. So for sub-elementary particles which are moving really fast, they may exhibit the wave-like character predominantly. Okay. Now the same thing is not true in the real world objects, like we are very heavy. Okay. So our momentum is tremendously large, therefore our wavelength is so small that it cannot be seen, cannot be understood or detected at all. So the wave-like character is a very useful thing for the subatomic world, but not for the real world, the bigger world. So the particle, I mean electron, will have the wave-like character as well. And this wave-like character will be equals to h upon p, or you can say mv, whatever you want to say. So we can actually treat electron as a wave without any loss of generality. So we can think like this. Sorry. Now coming back to the wave theory. So imagine this is a circular string and you create a jerk here. And this creates a wave which moves in two directions. If a wave will be produced in two directions because you are disturbing the medium, it will meet where? At this point, correct? And after meeting here, some part will reflect back. on both sides, and because of the reflection and the way which you are originating from this point, these two will superimpose, and as a result of this superposition, what they will create is a standing wave. So to understand this fact, we can draw a wall at the two ends of the string where the reflection will occur, and we can divide this into two parts. Each part will be having the length pi r, correct, because this is 2 pi r. So
Yes,
this
sir.
part, which is getting from going from here, will reflect and will superimpose and will create the standing wave like this. Now, from the theory of standing wave, what we know that the difference between the two nodes, this is called nodes, if you know.
Yes, sir.
These are, so between two nodes, the gap is lambda by 2. So exactly this is the de Broglie wavelength by 2, lambda d by 2. Understood? So this is lambda d by 2. And how many we can have? So depending on the excitation, it can be 1, 2, 3, 4. So it can be discrete. So it can be n values. Correct? So in general, the de Broglie wavelength upon 2 multiplied by n values must be equal to the pi r value. Is this clear? Lambda d upon 2, that is the length of the one loop. And if you combine n loops, then this will must cover the entire length of the thread, which is pi r.
Yes,
Is this
sir.
clear? So can we say that n lambda into d Broglie wavelength is 2 pi r? So that is a fundamental relation. This is the quantization of angular momentum, but this is still not evident that this is the quantization. So now to understand this quantization, let me just do one more step, and you will be realizing the birth of this formula. So n lambda d, let me write it this way, yeah, is so 2 pi r is n lambda d. So lambda d is how much? H by p, correct? So what is p into r? Nh by 2 pi, and the momentum into r is nothing but this is mvr, correct? So we know that this is the orbital angular momentum from the rotational dynamics. Okay. So if we have an electron moving in a circular path with velocity v at a distance r, so about the center, the orbital will be mvr, correct? I hope this is okay. So now this equation we call it quantization, and n we call principal quantum number. Okay. So this is the principal quantum number. mvr is equals to nh by 2 pi. I hope this is clear to everyone.
Yes, sir.
So every electron moving in a different orbit will have different energy or different quantum level. So n is the principal quantum number, and n we represent for orbits, right? So when you say n equals to 1, that is the first orbit or the lowest energy orbit. Then n equals to 2 will give you the higher energy orbit. 3 will give you the next higher. Fourth, next higher. Fifth, next higher. So the entire world of quantum theory is basically based on the concept of superposition theorem of wave, and everything is derived using the concept of standing wave or stationary wave. So in advanced level, we have some more rigorous derivations in 3 dimension as well. So this is the one-dimensional scenario. So later on, we'll also study that what if we use the spherical uh, shape. Now this is just a two-dimensional picture for you. So you're considering at nucleus as center and electron moving like this, which is rubbish because we don't have the flat atoms, isn't it? Or do we have?
No, sir, we don't have.
So this is just, these are all basic ridiculous assumptions. But if this is the beginning, we must study the history also, and from there we proceed. So now MVR is NH by 2 pi, and now using these two relations, the one which is the second, this is the second postulate. The first was circular orbit, which we have here, where we have, yeah, hmm, yes. So Coulomb's law is the fundamental governing equation here, and this equation is correct or right because we have the circular orbit. And now the quantization has come from the concept of standing wave, and therefore if you combine these two, we can derive the classical Bohr's theory formula. So no one should mug up the formula. Of course, if it, I mean, if you remember it by default, that's good. But in Bohr's theory, especially for the JE advance, you're supposed to derive from the scratch. Why? Because they may change some parameter. So once they will change some parameter, you need to rederive it. If they bring some twist to the theory, you need to rederive it. So let's say, let me show you one twist to the theory. So let's say I'm trying to create a new Bohr theory in which the atom concept is removed because this is just hypothetical. So I am saying that in my theory, the new hypothetical Bohr's theory, which I'm creating, okay, or J will create. So imagine this, in this hypothetical world, the atom is like a line. Now you cannot stop me from assuming this way. No, you can't. So I'm saying that the atom or the electron is confined to move between these two walls. And this wall is having the length A. So to begin with, we have to study the, I mean, start with the standing wave. So let's say the wave is formed this way, which upon superposition makes the standing wave like this. And because I'm assuming the electron to be confined in this wall, now coming back to the Bohr's theory, in Bohr's theory, we have multiple walls, wall 1, wall 2, wall 3. And what you can realize that every wall having different dimension. Do you realize this? So a Bohr theory is a collection of such wall or string. And in Bohr's theory, we have infinite number of strings of varying length. So we have one string, the first orbit, the second string, second orbit, the third string. And if you have studied the Schrodinger equation, you must have seen this length and graph. Hopefully. So, I mean, when they plot the graph, these are graphs, basically, these are graphs actually. So when they plot the graph, they use a line and they plot on the some wave. If you have seen the Schrodinger wave equation, right? So they keep the wall fixed and they keep on changing the mode of oscillation, or you can say the principal quantum number. So that is how they manage the various quantum numbers, and they plot on the same line, and you can see multiple graphs. If you have seen, someone has seen in the chemistry classes. So now in this new hypothesis, the electron is confined between the two wall and the separation is A. So to begin with, what we can say, that number of wave, like number of loop, you can say, into d Broglie upon 2 must be equals to how much? A. And here, because we have single length of string, so here as the energy level will change, the mode of oscillation will change. So you can get more number of lobes. You can get one lobe, two lobe, three lobe, four and five, and so on. So how much is the de Broglie wavelength? 2a by n. And the de Broglie wavelength is what? H by p. So what is the momentum part? nh by 2a. So what is the kinetic energy of this electron? Because it's a particle at the end. So what is the kinetic energy? So kinetic energy will be p square by 2m.
Yes.
Now can we talk about the potential energy here? Yes or no?
Yes, sir.
No. Because potential comes from the interaction of two charged particles, and what we have is single electron in a well. So here the kinetic energy is the only energy. Do you guys realize this?
Yes, sir.
Against the actual Bohr theory, where we have the nucleus and the electron, there you define potential. But if I'm giving you some hypothetical situation in which the electron is the only thing and it is only oscillating, so here the energy will be kinetic energy, and this kinetic energy will become the total energy of the system. So now this is the remarkable deviation from the classical theory. So the total energy of the oscillating electron will be equal to how much? P square by 2m. What is P square? N square h square by 4a square by 2m. So the energy turns out to be a very different formula. So what we can see that the energy is proportional to square of the principal quantum number, and basically the n is nothing but the mode of oscillation. So this is the square of n. So this is the principal quantum number which we call in physics. And now let's derive the same for the actual Bohr theory, which we are learning actually. This is the hypothetical situation in which the potential concept is not there, and it's very strange. Like we are missing the potential part. By virtue of the construct of the Bohr theory, we do have potential. That's very interesting because we have the configuration of two charges, and therefore potential is the thing in actual Bohr theory. So let's go and derive that. So coming back to the actual, and why we need to know all this thing what I'm describing. The reason is the moment J will make some twist to the theory, you will be like confused, like what to do now. So we should not have the one-dimensional thing. That Bohr's theory is not some, I mean, absolute theory, just one assumption, one model actually, and that is the creation of one individual called Niels Bohr. Then there are many such theories which came later on, and every model is one's hypothesis, one's assumption, one's imagination of the world, and that cannot be true because there was something called plum pudding model also, Thomson. Now, of course, that is totally rubbish, but yeah, that was someone's thinking at that time. That's okay. So imagine that by saying anything rubbish, you can become the greatest scientist in the world because no one dared to say that rubbish before. That's okay. So you can say any set of rubbish thing, but just like you should be in the right place to say this. So a commoner cannot say, but if you are the scientist, top-notch scientist, and if you are saying something rubbish, so people will listen to you. Oh yeah, you may get Nobel Prize as well. That's interesting. So in the actual Bohr theory, which is a set of circular, you can say wall or orbits, which is symbolic to the energy levels, not to get confused with real orbit. This is a model. Okay, so you guys should be clear with the concept of model. Models are just one individual's imagination, and that's okay. I'm okay with that. So it can be anywhere. It can excite to the next level, and so on. Okay. So now coming back here, we have two basic fundamental formula to begin with. The first is Coulomb's law, which is 1 upon 4 pi epsilon naught Z E into E upon R square, where R is the separation between the orbit and the center. And the other was MVR equals to NH by 2 pi, or you can see L equals to NH by 2 pi. Now there are multiple ways of writing the energy part. Okay, so if you want to write the kinetic energy, you can write P square by 2m. Okay, or you can write as P square R square by 2m R square, or you can write as L square by 2I. It's very simple conversion. So the momentum you can write like this, or like this, or like this. I is the moment of inertia of a particle from the center. So if you think of center as the axis passing through the center, and if you look at the electron at a distance r, the moment of inertia is how much? mr square. Is this clear? Hello, hello, 1 2 3 1 2 3. Is this clear, guys?
Yes,
Yes,
sir.
sir. Yes, sir.
So you can see that there are many ways in which you can write. No need to stick to one formula. You can just write P square by 2m if you are comfortable writing momentum part. But the best part which I use is the third equation. Why? Because L is directly known to us, right?
Yes, sir.
And therefore, because I prefer this one, so I cannot directly n square h square, or the n and h is sometimes confusing, so be careful about it, upon 4 pi square into 2i. Now let's substitute that also. N square h square upon 8 pi square m r. No, when I say r, it means the nth orbit. Okay, because n is the general quantum numbers, we can add nth orbit. So now we have the formula. Like you see, the kinetic energy formula we can got in one line. That's very interesting. N square h square by yeah 2i. Nice. But we can write in multiple ways also. So okay, because it's a interaction, so it will have potential. So can we write potential energy of two charges? So okay, of course you don't know. So it is k q1 q2 by separation. But in case of charged particle, when we write the potential energy, the rule is we must put the charge with its sign. Because there is an attraction, potential is bound to be negative. For repulsion, it is positive. In this case, what we should have? Positive or negative potential?
A negative potential.
And how much is that value? So it's k z square upon r. Or k you can substitute as, because we don't write k actually, 4 pi epsilon. Now this is the way of writing. That's okay. Can we write the kinetic energy in other way also? This is one way of writing kinetic energy. Can we write in other way? So we can write from the Coulomb's law equation, isn't it? What we can write? Tell me. From Coulomb's law, from circular motion concept, we can write net force towards the center is mv square by r. But this is same as kinetic energy into 2 times by r. Yes or no? Because half mv square is k, na? K is half mv square. So mv square can write as 2k, correct? I hope this is clear to all of you guys.
Yes, sir.
So once we have this, we can write we can substitute the Coulomb's formula, which we have already. So that is yeah, z e square upon 4 pi epsilon naught r square. Let's r. No, we can put r in it on just to write r square, and this is 2ke by r. This cancels, and there is a simplified answer of k. So we can write k in 2 ways. One from the Coulomb's and the other from the quantization. See, quantization itself gives one answer, and the force equation is giving you another answer for the same thing. So we have two stuff for one thing. So we are representing one same concept in 2 ways. So they must be equivalent, isn't it? So this answer, which I say answer 2, and this answer, which I say answer 1, because both are representing the same, can we say that these two must be equivalent to each other? Yes or no?
Yes, sir.
And if you equate these two answers, you will get the formula for radius of the orbit in one line. You can see, so simple, and it's not difficult. What I'm doing is I'm just writing the kinetic energy in 2 ways. One in terms of momentum and the principal quantum number, the n, and for that I use the quantization principle, the second postulate actually, and I'm getting the answer from the first postulate itself using the force and dynamics which we know. So what we are doing is we are kind of now matching the real world, the Coulomb's world, with the quantum world, and that is the first transition. I mean, that was the first thing that Bohr did. He brought the two world together, and he related these two. Now that was the model which made this possible, and that's why he won the Nobel Prize, because no one thought before that how to merge the two world, one the real world, the macro world, other the quantum world, and that was the first attempt. So we must congratulate and we must appreciate this effort by the Bohr. Although it's rubbish, but that's okay. So now let's bring these two together and let's get our first formula. And in fact, you can see the potential is not at all required, right? So are we using potential for the calculations? No. So the R calculation is very easy. Z E square upon how much is that? Sorry, and I don't remember any of this. You can derive whenever you want. It's so easy. So don't, when you're deriving, don't put any subscript because that will be just cumbersome. So just write simply write like this. Okay, and then we have this. So we got R equals to how much? N square H square epsilon naught upon m pi z E square, right? That's correct. Yeah. So you can write this as epsilon naught H square upon pi m E square whole into n square upon z. Now that is what we actually look for. the dependency. So Rn, now we can substitute Rn. We can write as Me with the mass of electron. Because that's confusing, I so I don't write, because you get confused with M and E, and that's a subscript actually. So now you can see there is a constant factor, and then there is a dependency, the variable part. So this constant factor, you can name it. What you can name? A. Now, why we are saying this is constant factor? Because it doesn't depend on any variable. So neither the uh, principal quantum number is a variable, because that is on the right side, and the Z. This is fundamental constant. That is the least radius possible in a quantum world, and that is possible when you put n equals to 1, because that is the first, the smallest orbit, and Z equals to 1, which is the H atom. So in the single electron system, for H atom in the ground state, n is 1, Z is any by 1. So the least radius possible is this value. So now this value is the least radius.
0.5.
Exactly. So that's 0.529. Yeah, correct. So the A value is epsilon naught h square upon pi me square, and this is equals to 0.529 angstrom. So this is the least radius possible, and or you can say that this is, at the same time you can say this is the radius of the orbiting electron in H atom in ground state. Is this clear? So for other atom, what will happen? Will it be lesser or more? So let's say if you go for lithium Li plus, this will decrease or this will increase. The smallest radius for the lithium will be more than this or less than this.
So less than this, right?
Less than this. Z is
Yeah, and now that's logical. I think you can also understand, because as you go to higher Z, the nuclear force will increase, and because
Yes,
the
sir.
nucleus is pulling it faster. I mean, like stronger. It means it will be closer to the nucleus. So definitely, as we go with increasing Z, we can see that the smallest radius will keep on diminishing, and that is quite logical. As per the circular motion concept, we know this. As the centripetal force will increase, you will have the small radius. Is this clear?
yes.
Yes, sir.
So everything is natural, and n is definitely, as you go away from the center, n will grow, and radius must grow with n. That's common sense. So even if you get confused in the examination, you should know at least that which will come in the numerator and which will come in the denominator, just in case you get confused. Logically, I mean, no need to like derive the formula. You can understand that as Z will grow, the radius must decrease, and as n will grow, the radius must increase. The only problem is that you need to remember the power of n also. Yeah, that it will increase the square of n. Understood? So now this is what you need to remember. But don't remember. I will suggest, okay, just try to understand the derivation part. In J advance in Bohr's theory, no amount of formula will help you in solving question. You have to you know, go back to the basic from scratch, derive the formula, derive the quantization part, because we have two postulates. So you have to derive the two postulates separately. And from that postulate, you have to derive the answer, not from the Bohr's theory. And the question that we just solved here on the last page. Okay, so you're not aware. This is the JE advanced problem. So this is not my problem. This is the JE advanced problem. And this is what I was teaching for a long time. And now JE eventually asked this question actually. So you need to know the derivation of two postulate only. And from there, you try to derive all other answers. Energy can be potential and kinetic, or sometimes it is only kinetic. Only potential is not possible, because if that is the case, then electron is not moving at all. So we don't have the concept of atom in which the electrons are not moving. Okay. So once you get the radius, I think we got the all other answer. So let's derive the total energy, because that's very, I mean, important. So total energy is nothing but the sum of potential and kinetic. So we'll derive these two first using the first postulate, the like basic physics. Don't use the quantum world. Quantum world we always substitute in the last. So let's derive from the basic. So in basic is simple. In basic, what you can say, un is minus 1 upon 4 pi epsilon naught ze square by ra. Yeah, that's fine. And in fact, kinetic energy we also got as a function of r. Yeah, this is the answer. Ze square by 8 pi epsilon naught r. And do you see a pattern? Both are almost same. The only difference is the factor. Can you see the factor?
Yes, sir.
What is the factor?
So half.
The factor is half.
Potential energy is twice of kinetic
Now this,
energy.
yeah. So this is what you need to remember. Just mug up. The kinetic energy is always mod of un by 2, half of the potential with mod sign. And this is true for all circular orbit. All circular orbit. Don't apply anywhere else. So whenever we have a model with circular orbit, this relation we can always write even for gravitation chapter or for this chapter or anywhere else. Now, why this is interesting and important? Because that will simplify the relation, that we need to think of kinetic energy formula to get the total energy. If you know the potential formula, because that is what we know easily from the basic electrostatics definition. So we can just write it down. So what we can write now is the En equals to how much? En is equals to minus Ze square upon 8 pi epsilon naught Ra. So this is the total energy of any orbiting electron as per the Bohr's postulate we have derived. Now do not take again this formula as in general formula. This is again a formula only meant for this model under these assumptions. If I change any of the assumption, I need to rederive the formula. And that is what you need to keep in your brain all the time. The moment you deviate from the assumption, we should not use any of the derived formula. Is this clear? Yes or no?
Yes.
Yes.
So let's go back. Look at this part. The R we have derived somewhere. Where? Do we have derived R? Where is R? Yeah, R is here only. So now this is R. Oh, this is R. So can we substitute the R value here and get the En formula? Minus Ze square 8 pi epsilon naught. Now comes the big formula epsilon naught H square. Okay, this is fine, right? So En equals to how much? So something will cancel out. Yeah, pi can cancel out. Anything else canceling out? No. So what we have is minus m e power 4 8 epsilon naught square H square, and now we have Z square upon N square. That is very interesting. So we have En equals to this value. So what do we call this value?
1.6.
Hmm?
minus
1.6.
13.6 electron
13.6.
This is called the Redebug constant, Hc, and you should know the formula in this way. And of course, the RHc is equals to what you said. And why we need to write this? Because in JEE advanced, question has been asked based on the Redebug constant. And then you can look at this R symbolic. What I have written is R infinity, because you will see two types of R later on: R infinity and R mu, or simply R. The R infinity assumes that, you know what it assumes? The nucleus is so heavy that it is essentially at rest, and the only thing moving is the electron. And when we derive under this assumption, we use a symbol R infinity. Because if this is not the case, if the nucleus and the negative charge are somewhat comparable mass, then the movement will be circular, but about center of mass, not about nucleus, isn't it? So in fact, you will have there will be two circles, one for nucleus, another for the orbiting negative charge. And in that case, we cannot use this formula. So the entire derivation will again collapse the moment nucleus starts moving. So none of the derivation that we have done so far can be employed at all. And there comes this rescue operation. The rescue operation is write the formula in terms of R and you will be saved. How? Look at this. I should leave this. Yeah. So next part. So there are too many ifs and buts. Like the moment I make any small change, the entire thing collapses. And why n is in the denominator? Any guess? Intuitively, what is happening here? Any guess?
So it is negative, so it would be directly proportional to n. Right? That's
Now tell me, as you go away from the nucleus, the energy will increase or decrease? That's it. What is the question? So as you go away from
increase.
the energy must increase. And if n will increase, energy will increase. How it is possible? The numerator or the denominator?
So sorry, will you repeat that?
Pardon?
So please will you repeat the question?
Question is like, we know that as n will grow, the energy must grow. But here the relation is inversely proportional. Why it is so?
so negative sign.
Exactly. So it is a negative sign which is playing the role of reverse. So to make value bigger with n, it must be in the denominator. Now, if it is a plus sign, then of course n must be in the numerator. But luckily here we have minus sign, and so n must come in the denominator. And again, that is a way you can always understand or remember in the examination, that the moment you get confused, these thing will help you in recalling the formula in the correct way. Okay. So energy in the nth orbit is RHc z square by, and definitely what is RHc? That's big value, me power 4. And again, I don't remember anything. I just derive in the exam class, and that's it. And I don't expect anyone will remember this. So the Redebug constant, we have a formula m. All right. So what happens if we have a situation in which the nucleus is also moving in a circular path? How to modify all of the Bohr's formula that we have derived so far? So let me derive all formula first, then I'll go to the situation where situation will change and this formula will collapse. But we can rescue easily. There is a way to rescue. So can we derive the formula for we have derived formula for energy, radius. Now I'm looking for velocity. So what is the formula for velocity? I want v. So for that matter, I'll go to the formula which is mvr is n h by 2 pi. Okay, and I think that is sufficient. Because the reason is clear. We have a kinetic energy formula already. We can get from there also. But anyway, so what is Vn? nh2 pi mRn, and we have derived Rn. So let's substitute nh2 pi m. And what is Rn? You know the answer. Epsilon naught. What is Rn? H square upon pi m square. Oh, that's not difficult. Pi m square into n square by z. Oh, that's nice. M will cancel out, pi will cancel out. Oh, that's even nicer. So what we are left with? H will also cancel out. Oh, that's great. So we have Vn equals to E square 2 epsilon naught H. Yeah, that's really cool.
Yeah.
And the rest is simple Z by N. And this should be now because the energy is Z square by N square. So half M square is proportional to this value. So V will be proportional to Z by N. So the proportionalization is anyway easy to remember, but this is the derivation. And what is this value? E square 2 epsilon naught H. Any idea?
Is 2.186 into 10 to the power 6 meter per second.
2.10
186
power
6 meter per second.
meter per second. So the electrons are moving really fast, 10 power 6. Okay. So as n will grow, v will decrease. So when n tends to infinity, v tends to, which simply means that you're not under the attraction of nucleus at all. So you're not supposed to move. Simple. That's the meaning. N is infinity, it means you are so far from the nucleus that the nucleus will almost stop acting on the particle, on the electron, and therefore there is no centripetal force. So you do not need to move in a circular orbit to maintain the orbit. You can be stationary, you can be there forever, but that's the meaning you are leaving the atom. That's the other way of thinking. Next part. So once you know this formula, you can find the omega, you can find the frequency, and this I'm leaving as an exercise. Okay, you can do this. So what I'm looking for is the situation part, okay, which we just discussed. So what happens if things goes wrong? So what if nucleus is also moving? Now that happens when the positive charge, which is the generally nucleus, and a negative charge. So far we had electron, yeah. But let me make a twist. So let me introduce a new particle and I'm naming this as muons. Now muons are basically roughly 200 times mass of electron, and we know that mass of electron is roughly something like this, 1837 or whatever. You can just verify this number. So the mass of electron is m mass of proton upon this value. But if I make 200 times, which is the mass of muon, this is become like 18 by 200. So you can make it 200 here and 1800 here for the simplicity. And this is not a small mass. This is comparable mass. So if we have a mass m and if we have mass m by 9, do we expect the center to be here or somewhere here? So we need to divide this into 10 parts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I can say this is the part where the center will lie, center of mass. And now this nucleus will move in this orbit, although very small, but that's okay. And this will move in a big orbit. Yeah, that's fine. I hope you got the crux what I'm trying to say.
The center will be center of mass only.
Yeah, the center will be center of mass only. So now the nucleus is not the center. Understood? So look, let me make it more meaningful by drawing a small scale diagram. So if we have a two charge particle with comparable mass, then the concept of circular orbit is still intact. So the Bohr theory is not going to fail, but we need some modification to make it correct. So the moment we have the comparable mass like m and m, then we bring the concept of a reduced mass. And the rescue operation is simple. You derive the answer in terms of Redebug constant, because that's why I wrote everything in terms of Redebug constant. And then the relation is simple. If you remember the Redebug constant, which is here, this constant is proportional to mass. So here we say the R mu is proportional to mu, and R infinity is proportional to m or me basically, which is mass of electron, and therefore the R infinity, or you can say R mu upon R infinity is mu upon m, and therefore you can say R mu is how much? So the small change which you need to bring here is replace all the R infinity by R mu, and then, or you can say just multiply with this factor to the formula, you'll get the answer. So this is as good as saying that the m term in every formula should be replaced by the reduced mass. The moment you do so, all the formula which you derived earlier again will be correct, and now you can apply for the further processing. Is this clear? So when Bohr's theory will collapse, so first is one, it will deviate from the two postulates. The moment you deviate from the two postulate, the formula which we are deriving, the classical formula we are deriving, this formula will not valid. Okay, I'm not saying the Bohr's theory is invalid. Bohr's theory will have now some other modified formula. So things to be noted down. First, you know the classical value. That's okay. And second is always know when not to apply. If you are clear with the concept that when not to apply, the chance of making mistake is really small. Okay. So this is one part. And again, of course, when question will come, you can do this modification to get the new answer. Again, I'm leaving this as an exercise. And the next part. So now we'll talk about the transition. So transition of electron in classical. So in this case, so now we have a formula En equals to minus RHC by into okay. So every orbit will have its own energy level, and Bohr said that okay, electrons are only allowed to move in orbit with fixed energy values. So if you stay in the, let's say, some random orbit, nth and mth. So if you live in the orbit n, the energy value will have this value. When you go to the orbit m, then you cannot have the same energy. You have to live with this energy. So every orbit will demand some energy. So if you want to go from the low energy level to high energy level, then the difference of energy must be provided by some means. Okay, that may be by absorbing the you can say some energy in terms of electromagnetic radiation. So you can absorb h nu and go there. Okay. Or the reverse process may occur that if you jump from the high to low, then you cannot keep the extra energy with yourself. So the moment there is a transition, so if the electron goes from low orbit, the extra energy you cannot keep with yourself, so you have to transmit or radiate, and that is how the h nu comes into the picture. So every transition will always lead to the release of energy. You can think like this guy suicides, and this is the soul leaving the guy. Okay, anyway, that's just joke. So this is the soul, okay, the energy part, because you cannot keep that energy. So that energy you must release, and that is how the light is produced in real life. So every source of light undergoes this kind of transition to produce light, and therefore the white light is composed of variety of transition, in fact all possible transition, and that is why we get a big spectrum. We don't get a discrete light. So you must be understanding that when we try to produce a laser light, which is a monochromatic, we must make sure that we have single transition. Only one type of transition will bring the one type of color of frequency, because it is impossible to make sure this event. Therefore, it is impossible to produce perfect monochromatic light. So when we say monochromatic, it is basically called quasi monochromatic, which simply means it is roughly monochromatic, not exactly, because that is impossible. So in the real world, we cannot produce this. Now we can, of course, achieve a state when it is close to the monochromatic. So we can improve the degree. And I think in 2020 or 19, the Nobel Prize actually given to the scientist who produced the blue laser actually, and that was almost pure light. Almost means the accuracy was much better than before, and he got the Nobel Prize for that material, because you need to develop the material which can make this transition possible. So here comes the concept of material science and so many things. So it is almost very complex. I mean, this is almost next to impossible that how you can make sure that the atoms will behave in this particular way, because we cannot deal with atom, we deal with the matter. Anyway, so that's the big research. So now there are two things. If you want to know the energy value, so you need to subtract the energy of the high from the low, and the moment you do so, this will result into the energy Sc by lambda. You can write this Sc by lambda, and this lambda is not the de Broglie. This is the actual wavelength. This is the electromagnetic wave. This is the energy of, oh, I should write here, energy of EM wave released in the due process.
So M is
Okay.
the high energy orbital, na? And N is the lower energy.
Yeah. This is high. But because of the minus sign, it will reverse, right? So because it's minus sign, so what you will get is n square minus m square. Understood? Is this clear?
Yes, sir.
Now, in case of atom, what we know that if this is the nucleus, and as you go, initial the gap is big. Now the gap will decrease. Let me draw the first orbit. Second is closer. Third is even closer. Fourth is fifth. So the last will be like something like this. So now the question is, as you go far away, the successive energy difference will decrease or increase?
Decrease.
Yeah, decrease. So now there will be a point where the energy will be so small that the energy release will lead to which kind of you can say spectrum? Visible. Now we have multiple. Of course, we have a like infrared. We have then visible. Then we have ultraviolet. Then we have, you can say, uh, ultraviolet, X-ray. No, gamma ray. No, gamma is much more than X-ray. Then gamma ray, and then cosmic rays. So the energy will change accordingly. So the whole idea is, as you make the successive difference, the energy will fall below the visible spectrum eventually. Okay. So not all transitions will be observable by the human. We can only observe certain transition, and therefore we have the different spectrum defined, and that this different spectrum we call the Lyman series, Balmer series, Paschen, Pfund, Humphrey. So you know the various series name, right? Because these series names are basically based on the variety of energy that we can get and the reason in the electromagnetic spectrum where they fall. Okay. So this all depends on the orbit number, n values. Okay, and the successive value may decrease. So you may be asked a question that let's say if we have a device which can detect this particular wavelength. So they will mention some name of the wavelength, X, Y, Z, whatever, and they will ask you that which two possible transitions or which quantum number can give the energy which can be detected. So what is the maximum value of quantum number which can detect that energy? So maximum is how far you can go from the nucleus to the orbit and you make some transition, one step transition, which can be detected. So we know that this energy is big energy, now is smaller, now is smaller, now is smaller. So beyond certain transition, the energy cannot be detected also, because we have a certain device which can detect up to certain wavelength. So if it will go beyond that, then we will fail to detect. Understood? Those questions are there in the SC itself, and if you solve, you'll get to know those things. That's why we're discussing here. Now you can see this HC will cancel out. So what we are getting from
Set lambda to the lowest or
lambda to the
highest visible.
lambda will grow actually. It will become infrared. As energy will decrease, lambda will
Increase, yes.
increase. Na? Bigger lambda is less energy. Frequency, more frequency is more energy, but more wavelength is less energy. Correct?
Yes.
Yes, sir.
And now you get a formula which is a very famous formula: 1 by lambda equals to R infinity 1 by n square 1 by m square. Now in this chapter, this is the formula we should start with, and then you can go on reverse. How? If you multiply by Hc, what will you get? Energy relation,
Energy.
and everything else you can derive from this formula. So this is the backward formula derivation, and this is easy to remember. It is 1 by lambda is R infinity, because the dimension of Redebug constant is inverse of wavelength, which is L inverse, right? So dimensionally, this is length inverse, correct?
Yeah.
Yeah. So you should know that
Yeah.
Redebug constant is just inverse of length, and you may be asked some dimensional formula, and just you need to remember this Redebug formula dimension relation. That's not very difficult. And now, and even the value of this is very simple to remember. It's 1. I think 0.7 10 0.7 or 0.1, I think 10 to the power minus 7, I think plus 7. This is inverse. Yeah. So it is 1.01 10 power minus, 10 power plus 7. That is the Redebug constant value. You can just check it out. Maybe some decimal place I am missing. 1.01, I think something. 1.05. Okay. So even you should remember the formula of Redebug constant. Okay. Next one. Now there's some terminology which I used, like first excitation energy. What is first? So what is excitation energy? So excitation means to go from the ground to any other state is called excitation. So when we say excitation, it means the first level must be ground, and then you can choose the other level. Okay. So when I say first excitation state, then you go 1 to 2, and then when I say second, then you go 1 to 3. When I say third, then 1 to 4, and so on. Is this clear?
Yes,
Hello,
sir.
hello. Now, when I say
Yes.
first, let's say if I'm saying an electron is in first excited state, what does it mean?
So it is in second orbital.
Yeah, it is in second orbit, correct. So these terminologies are very important. The next is ionization energy. So what is I meaning? I think this is chemistry thing, so I should not teach also. So what is ionization energy?
To remove an electron from an
Energy.
orbital.
From the
From the
Last orbit.
orbital.
valence shell, right?
Valence shell.
So valence shell means the where is the last electron? That's it. In the ground configuration. So ionization energy doesn't mean that you put the electron in the excited state and then you remove. Then you can't say it's excited. I mean ionization. Ionization means if we know that my electron is in the valence shell in the normal configuration, then how much energy we need to remove? Okay. But what happens if the electron is in excited state and then I want to ionize? Then the ionization energy will be less than actual. True or false?
So can you repeat question?
If the electron is already in some excited state, okay, and then you ionize it, or you want to remove it from the atom, then the amount of ionization energy will be less than actual value. Yes or no? True or false?
Yes, sir. This will be less than actual value.
Yeah. So now they may give you many combination, like this will be like a word problem. So they will give you that the first excitation energy is equivalent to the ionization energy to remove the electron from the second excited state. So you need to convert this word into a mathematical framework. Understood? So how much energy we need to remove? I mean, we need to remove electron from the third excited state. How to write this in mathematical terms? So imagine this question, the basic question. So we have single electron system as we are learning this part only. So electron is here. Tell me, if it is H atom in ground state, how much energy we must supply to remove this electron completely? So we have to ionize it. So what is the ionization energy? Tell me. Here we have only ion because
So
there is no second.
13.36 electron volts.
6 electrons.
So
13.6 eV,
2.184.
right?
Yes.
Yes, sir.
And if you look carefully, this is nothing but the mode of energy of the first orbit. Do you realize this?
Yes, sir.
It's the mode of energy of the first orbit. Similarly, but what happens if the electron goes here? It is already in the excited state, and now I want to remove it. Then what I can say about the ionization energy here for this case? Then I cannot say 13.6 because already I am having some excitement. I mean before, so we just need the difference of the energy, and that is exactly equals to mod of E2. So if you take the mod of this energy level, that is sufficient to remove. That's it. So what does it mean is whatever negative energy you have in that orbit, you supply that much positive and that you can remove. That's the idea. So if you are in any energy level, E1, E2, E3, these are energy levels, and we know all are negative values, correct? These all are negative. So to remove the electron from any orbit, you just supply the positive value from there. That's it. So to remove from the first orbit, you need to supply the positive of this value. So that's why I'm writing mod actually, because by default these are negative values. So when I put a mod, it becomes positive. So if you give that energy, it will remove. That's the only idea. Is this clear? Yes or no?
Yes, sir.
So you have to convert this word problem into a mathematical framework, and then you can solve any question with ease. So read the question carefully, try to convert into some mathematical framework, and then solve it. So now to end this Bohr's theory, we'll do some practice about energy levels. That's very important and interesting. And we'll do it for only H atom. So for H atom, what you are supposed to remember to master this chapter? Remember the energy level of all orbit up to 10. So how many level you remember? That's not difficult, but you can remember. Oh, I think sufficient. 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's less. 9, 10. Yeah. So this is n equals to 1, n equals to 2, 3, 4, and there is a magic. You can remember every answer easily. That's interesting. Yeah. So to begin with, n equals to 1. Yeah. Tell me the answer. Minus 13.6. Correct. And the formula is pretty much obvious. It's 13.6, and because it's H atoms, Z is 1 upon n square. So next will be this upon 4, which is minus 3.4, right? Let's
Yes.
check it out. Then what is next?
1.5
Hmm?
1.56.
minus 1.5.
Minus 1.56.
6.
6 or 1? Let's check. 9. 13.6 by 9 is how much?
Minus 1.5.
13.6 by 9. 1.51. Yeah, I was right. Yes. What is next?
minus 0.85,
What is next?
minus 0.54,
5. Correct. 5. My bad. The next, what is next? 37, 21, 16 or 17 roughly, 16 something. Then I think something in between. Is it 27? 27? Just check. Then this is 21. Hopefully,
yes sir, 21,
this is 2. After 0.37, what is next?
sir 27,
27. Correct. 27. Then 21, and then 16 or 17, like 16 something, and then we have 13. Yeah, correct. Now this is not difficult to remember. Just revise once or two, so you can remember every value. There is a rhythm: 13.6, 3.4, 1.5, 1.85, 0.54, 37, 27, 21, 16, 136. And now do this practice. Everyone, let's start. The first two is just cover this. Don't see this. Let me remove and let me just hide this.
We were taught by remembering it as a phone number of 10 digits.
Yes, yes. So remember this entire value. You can do it in this small practice and you can remember everything. How many of you remember all values? Everyone. So let's start with the first is 13.6. Next is, tell me. Next value.
0.65
Next is
3.4.
3.4.
minus 3.2.
No, don't say minus. Like that's okay. We know the it's minus. 13.6, 3.4. What is next?
1.57.
1.5.
1.551 because 51.
Half.
51. It started with 51. 554 will come later on. What is next?
0.85.
85. Yeah, 85. Then what is next? Think about it. 85. Then reduce it. 30. 85. Then next is 54. Yeah, 54. The next is 37, 27, 21, 16, 13. That's it. 13.6, 1.36. This is not difficult. This is so easy to remember. This is something magical. I mean, anyone can read once and remember this forever. Is this clear, guys? Yes or no?
yes sir,
Yes, sir.
So once you remember, what are the benefits? The benefit is you can always do it for any other atom because the only difference is Z square. Correct? Because we know the formula is En is. So if you remember the H formula, then if you multiply with Z square, you can get any other answer for lithium, for beryllium, for helium plus. You can do it for any other atom. So we just remember one formula, and for the other level, let's say if I want to write the lithium plus, just multiply with the 9 to every value. So 9 into 9 into 9 and so on. For helium, 4, 4, 4 to every value. And so on for beryllium, 16, 16, 16 for every other value. Now, what else we need to remember to solve the question efficiently? You need to remember the difference value. What is the E1, which is very famous, the first excitation energy? Okay. So how much energy you need to give to go from here to here? This is E1.
10.8.
11.2,
10.2.
sorry 10.2,
E1 is 10.2 eV. Now this answer is very famous. So the moment you see this number, you should be able to guess that, okay, this is the first transition energy. Now, the first transition energy is always the biggest energy because we know that successive difference will only decrease. So always remember, if any number is huge, close to the 13.6, it is the first transition. Now, what is E2 value? How much we need to go from the first to the third? Tell me, guys. What is E2? It's very simple. Hello, hello, 1, 2, 3. Am I audible, guys?
Yes, sir. 1 minute.
Yeah. Tell me the E2 value quickly. What happened?
12.09.
So you should remember this answer. This is something. See, in Bohr's theory, if you don't remember the values, it's almost difficult to solve the question easily. So remember the E3 also. What is E3? Check the E3. What is E3? I think this is the answer. This should be the answer.
12.7.
And the last, what is E4? What is E4?
13.06.
How much?
13.06.
Very good. Now, these 4 answers you must remember. First thing. What else we need to remember? Remember the successive difference. So let's find the how much we need to go from 1 to 2. So the first E1 is same as the E1 minus E2, right? E2 minus E1. It's the same thing. So if I want to know what is E3 minus E2, then what we need to do? You can just find the value. What is 3 minus 2? Or 3, yeah, 2 minus 2, correct. How much is that? 3.4 minus 1.51. How much is this? Is it 2.89? Just check. Is it 2.89? I think this should be. This is. I think this should be the answer. Just check. Right?
Yes.
So 1.8.
1.89. Yes. Yeah. Yes. Correct. Now, what is the value of the next transition? Let me just. What is E4 minus E3?
So
4 minus
0.66.
point.
66.
I mean, you just check. I mean, I'm trusting your words. Now, let me take a difference. So 1.51 minus 0.85, yeah? 0.66 is the right answer.
Yes, sir.
And what is, yeah. And the last answer is 5 minus 4. How much? Point?
0.31.
Okay. Now, why we need to remember this answer? Let's say I'm giving you a question. So in a certain transition, a photon is released with energy 1.89. This should click that this is released because the electron was in third excited state, I mean third level, that is the second excited state, and it came down to the second, and that's why the energy difference was released. Now these values 1.89, 0.66, these are very famous. Let's say take some other answer. Just so some other values which we need to remember. Let's say what happens if the electron will transit from the 5 to second, 5 to 4, or like these values. So of course these are Lyman-Balmer series. So I hope, because that part is covered in the chemistry, so I'm leaving this part. So do you want the series part to be done here? Lyman, Balmer, Paschen, Piffen, Humphrey.
Yes, sir, it's fine.
So you know the spectrum number of spectral lines released during the transition.
Yes. N into N plus 1.
Yes. So let's make a. I'll show it for the 4. Maybe this will help you in one way or the other way. Okay, n equals to 1, n equals to 2. So let me plot all the lines that is possible. So first of all, we all will try to go from the top to the bottom. So which line is this? Lyman, Balmer, Paschen, Piffen. Which one I have drawn here? Tell me.
6 Lyman.
This is Lyman. Correct. This is UV. Okay. Okay. So then we have Balmer, which is the visible region.
Yes, sir.
So it will start from here, but it will stop here only. Stop. Stop. So the green one is the Balmer. Okay. And then we have the infrared. And then it is near infra, far infra, very far infra. But everything is not infra only, because you are making a transition only to the. So here 1 and 2. So if I draw more lines, you can draw more lines. Now, question was, there was a question. So an electron is in the 5th orbit. So let's say there is an electron here. And of course, it can go down. So what are the possible number, like how many visible lines will be released, visual spectrum?
15.
Just 3 values. There are just 3 possible frequencies released in the visible spectrum. Because you can see that if you're in the 5, we can only draw 3 lines like this. And this is visible, right? How many UV will be released in this process? Possible values?
0.
4. If
Okay,
you're in the
from
5th
5.
orbit, pardon?
Sorry, nothing.
If you are in the 5th orbit and if you go down, like there are infinite atoms in the 5th orbit, I mean, we have electrons in the 5th orbit, there are multiple transition possible. I'm saying how many distinct visible lines will be released? So answer is 3. If I ask you how many distinct UV lines will be released, answer is 4. And how many distinct infrared will be released? Answer is just 2. And if you add all this, I mean 4, 3, 7 to 9, if you add all values, there is one more, no? We can have one more, the far infra, from here to here, right? That's it. Count every value. How many values we have? Check. 10. And that is exactly 5C2, which is 10. Understood? So when something is in the 5th orbit, then multiple things can be done. Okay. So let's say if I have an electron in the ground state, try to understand this problem. This is the question actually. And if I give sufficient energy such that it goes to the 5th state here. So first you supply the energy, it goes there. Once it reaches the topmost point, like the 5th orbit, it can come down in a variety of ways. So the question is, when it will come down, then what are the possible varieties of spectrum it will release? So you can see that we have 3 infra, because I'm combining all types of infra to a single infra. We have 3 visible, and we have 4 UV. So these are possible transition. So you may throw to the topmost point, but coming down its own virtues. It will come down with its own nature, randomness. We cannot decide anything, and therefore these all possible transitions are there and could be possible, and therefore you will get Lyman, like 4 distinct values of Lyman if you can observe, 3 distinct values of visible, and 3 distinct values of infrared, including far, near, all infrared. Okay. So similarly, if someone will tell you that if the electron is in the 6th, because I mean they will always give you the answer which you can calculate, not a big deal. So from the 6th, how many visible is possible? So if it will come down to the ground state in the due process, how many distinct visible lines are possible? The answer is, tell me quickly.
4.
How many?
4.
4. Very good. Now this is the question that you will be asked in the examination. They will not ask you the number of transition. They will not ask you the number of spectral lines, which is because that's easy. Now anyone can do NC2. What they're asking is different. What they're asking is the visible lines only, or the UV lines only, or the infra only. Then you have to do this calculation. Or it's good to draw the diagram like this, and then you can count it. That's very easy, super easy. So in this particular case, that's very important. Hello. Hello.
Yes,
Hello.
sir.
1, 2, 3. All right.
So what did you ask for, which the answer was 4?
I asked that if the electron is given the enough energy to reach the 6th orbit or the 5th excited state, as you can say, and then it definitely it will try to go back to the ground state, right? That's the natural process. So in the due process of going down to the ground state to achieve the most stable energy configuration, how many distinct visible lines will be released? Question is clear?
Yeah, so
Distinct visible lines. So how many will be there? If you come from the 6th orbit, just draw this. Now this is not difficult. 1, 2, 3. 4. So 1. Okay, visual means you go only up to which level? First, na? Here. You can go from here to here. Here. Count how many? 4.
yeah,
Because
sir.
the Balmer is 4, na? So the Balmer is the visible. The Lyman is the UV rays. So with that we don't count. And you can see there is a huge energy difference between the 2 and first that we have seen already. That's 10.2 EV. So the moment you add this energy, the energy spectrum will change from visible to the ultraviolet region. Understood? So that's the whole idea. I hope this part is clear.
Yes, sir.
So, I mean, of course, I mean, the best question you will get in SC Verma. So I will say that everyone must solve each and every question of SC Verma, and then you can discuss with me the doubts, because there are some really interesting problem, and just try to solve this. And there are many conceptual problems. So you need to solve objective 1, then solve objective 2, then solve exercise, and that is more than sufficient for G advance. That takes care of everything. Okay. So rest you can ask in doubt lecture or tutorial, or if you want you can ask me also. Okay. So this I'm taking this part because I'm taking the monophys. You can ask me also. That's not an issue. So this is the end of the Bohr's theory. I mean, you do the derivation, go home, do the derivation. I'll share the nuclear. I mean, this the Bohr's theory lecture question sheet very soon, and you can start practicing. But the best thing is start with SC Verma. Once it is done, then do anything else, because that is more than sufficient in my thought. Okay, see you in the next lecture. Bye guys, and take care.
Bye, so thank you.
Bye, sir. Thank you, sir.